Okay, so this video is sort of intended to help get ready for the test, but also to reinforce some of the concepts that we used in homework 2, maybe some of the harder ones in particular, because I think that would be helpful. So I'm going to prove a number of things here. And I encourage you to take a look at the theorem I'm about to prove and think about how to prove it yourself, and maybe pause the video and really think about it. But like before I give any hints or really get into how to do it. So the first one just says if the minimum degree of a graph is at least n over 2, and by the way, you probably noticed I almost always use the letter n for the order of a graph. If I ever use the letter n but I don't make it clear what n is, it's probably the order of the graph, but this time I remembered to write G has order n. So the minimum degree is at least n over 2, and it's a graph of order n, and we want to prove that that means the graph is connected and that the diameter of G is less than or equal to 2. So about this, first of all, if we can just prove that the diameter is less than or equal to 2, then that shows that it's connected. Having a diameter at least 2 means that if I have any two vertices in the graph, that their distance at most 2 from each other. And of course that means it's connected. To be connected, I just need to know that between any two vertices there's a path from one to the other. This is telling me that there's a path of length at most 2. In fact, if I could just show that the diameter is finite at all, even if I show that the diameter is at most 10 or at most 1,000,000, that would show that G is connected. So it's certainly enough to show that the diameter is at most 2. So we won't worry about showing that G is connected. We'll show this part, and that automatically means it's connected. And right, so I wrote something that I wanted to cover up for the beginning, just for the people who wanted to think about this and think about how they would prove it, but maybe I'll uncover this now. So I'm going to prove the following claim, that if I have two vertices, u and v, and the degree of u plus the degree of v is at least n minus 1, then the distance from u to v is at most 2. And the reason why I'm doing this problem is kind of to reinforce this idea of vertices having common neighbors. That was part of the solution to the homework. Here's what we're going to do. To show that two vertices have distance at most 2, well, there's really only a couple of ways it could look if it's distance at most 2. The distance could be 0 or 1 or 2, right? Distance 0 just means it's the same vertex. Distance 0 can only happen if u equals v. Distance 1 happens when they're different vertices, but there's an edge going directly from u to v. That's what distance 1 vertices look like. Two vertices have distance 1 if and only if they're adjacent to each other. Distance 2 means that they have a common neighbor. Distance 2 means that there's some third vertex, say w, such that you can go from u to w to v. and W would be the common neighbor. So let me prove this claim. And like I was saying, I have in mind the possibilities for smaller diameters. And the first thing I have in mind is diameter 0. If they're the same vertex, then the distance is 0. So we're done in that case. Another possibility is we could have a distance of 1, and that happens if they're not equal, but UV is an edge of G. And that means the distance is 1, and so once again we would be done. Okay, so then what if we don't have either of the things that we just mentioned? So assume that U is not equal to V. So I'm not in this first case, and I'm also not in the second case. So U is not equal to V, and I'll assume that UV is not an edge. What I have to do from here is prove that the distance from U to V is still at most 2. And what I'm going to do is show that they have a common neighbor. So how is this done? I know information about the degrees of vertices. The degree of every vertex in the entire graph is at least n over 2. And so, roughly speaking, actually, I can start to draw a picture down here. I've got U, I've got V. When I'm drawing a graph and I want to emphasize that an edge is not there, I sort of draw a dotted line. So I'm going to draw a dotted line because we're assuming that UV is not an edge. And once again, my goal here is to show that they have a common neighbor. And why don't we try doing this by contradiction? So let's assume they don't have a common neighbor. That means if I draw the neighborhood of U and the neighborhood of V, that they don't overlap at all. And before I get too far ahead of myself in the picture, let me write some more stuff for the proof. And okay. For the sake of contradiction, because once again we're trying to show that U and V have a common neighbor, let's assume that they don't. Then so we get the contradiction we're looking for just by counting the vertices in the graph. First of all, the number of vertices is supposed to just be n. But looking at the picture and thinking about what we know, let's count the number of different vertices that we already know about. There's U, there's V, that's 2, plus there's this set and there's this set. And we know that they don't overlap, or that's our assumption right now anyway. They don't overlap. So if I want to count all the vertices, I can really just add this many plus this many. If they were overlapping, then I would have to subtract how big is the intersection, but they're not overlapping, so I can really just do this much plus this much. This is the neighbors of U, and we know there's at least n over 2 of those. This is the neighbors of V, and we know there's at least n over 2 of those. So we just showed that n is greater than or equal to 2 plus n. That is a contradiction. It makes no sense. So that means U and V do have a common neighbor. And that means the distance from U to V is exactly 2. Right, I mean, maybe I'll just draw a little picture here, but you probably know what I mean. There's no edge from U to V, but there is an edge from U to W and from W to V. So I can get there in 2 steps. It's not possible to get in 1 step, but I can get there in 2 steps. And just going back to the big picture, let's say oops. Oh, sorry. Hang on. I made a little mistake here. I was trying to prove this claim, which is part of proving this theorem. So let me be a little bit more careful here. Yeah, so the issue is with these n over 2's. I made a little mistake here. Going back to what I was saying, we were counting the vertices, and I said I have 2 here, U and V, and then I have this many plus this many. I shouldn't have written an n over 2 here. What I should have written is the degree of U and the degree of V. And then that shouldn't have been that. What I should have used is what the claim actually says. The claim says that the degree of U plus the degree of V is at least n minus 1. So here I get 2 plus n minus 1, which is n plus 1. And that's still a contradiction. N is not greater than or equal to n plus 1. So sorry about that. It just got a little bit confused about which one of these things I was proving. I was proving the claim, and now this proof should be correct. We still need to prove the theorem, but we're basically done now that we have the claim. So actually, maybe I'll just put a little proof box. But that's just the proof of the claim. Now we have to prove the theorem. The theorem says the minimum degree is at least n over 2, and we want to show that the diameter is less than or equal to 2. What we have is a claim that tells me that the distance between 2 vertices is less than or equal to 2, and that should be very nice if we want to show that the diameter is at most 2. Let U and V be any vertices in G. We're just going to use the claim. First, let's check that we can use the claim. In this one, I am assuming this, that the minimum degree is at least n over 2. So the degree of u is at least n over 2. The degree of v is also at least n over 2. And so that makes n. And in order to use the claim, that just needs to be greater than or equal to n minus 1. So that's true. So since the degree of u plus the degree of v is at least n minus 1, we know the distance from u to v is at most 2. Since u and v were arbitrary vertices, they could have been any two vertices in the graph, and the diameter is supposed to be the longest distance or the largest distance between any two vertices. We showed that any two vertices have distance at most 2, so then that means the diameter is at most 2. Okay, and as we discussed, that means the graph is connected. Okay, so for the next one, let's do this, and I'm doing this because this is like a slightly easier version of one from the homework. On the homework, we had a problem that said if the minimum degree of a graph is at least, I think it was 2n plus 1 over 3, then every edge of the graph is in a complete subgraph of order 4. This time, we have a different minimum degree. It's n plus 1 over 2, and what we're proving is that every edge in G is in a complete subgraph of order 3, in other words, a triangle. So yeah, I encourage you to pause the video and think about how you would do this before I go on, but I'll just assume that you did that. Let's prove this. So suppose this, and we have to prove that every edge is in a triangle, so consider an edge. Say, I'll name this edge, the way we name edges often is by the names of its endpoints. So say the endpoints are x and y, and say that's an edge of G. We'll show xy is in a triangle. A triangle just means 3 vertices that are all adjacent. I already know that x and y are adjacent to each other, so I just have to find a third vertex that's adjacent to both x and y. In other words, I have to find a common neighbor of x and y. So I can start drawing a picture. And why don't we say we're going to prove this by contradiction? So I'm going to draw a familiar looking picture here. A is meant to be the neighborhood of x, B is the neighborhood of y. Whoops, I drew a dotted line. I should draw a solid line because x and y are adjacent. And right, the meaning of these bubbles is that x is supposed to be adjacent to all of these and y is adjacent to all of these. And I drew them non-overlapping because I'm going to go for a proof by contradiction. Of course, I want them to be overlapping because if they overlap, then I can just choose a vertex in the intersection and that vertex will make a triangle with x and y. But I'm going to go by contradiction, so let's assume that they don't overlap. So let me write something before I get too far ahead of myself. Let A be, okay, when I was talking out loud, I think I said A is the neighborhood of x, but actually the neighborhood of x would also include y, and I don't want that to be an A, so here's what I'm going to say. A is all the neighbors of x except for y. And I wrote that this way. This is set subtraction. This means that here's the set of all neighbors of x, and this means I'm removing y. And let B be the neighbors of y except for x. And assume for the sake of contradiction that they don't overlap. In other words, the intersection is empty. Then what am I going to do? I'm going to count the vertices again. Well, first of all, there's just n vertices. But how many different vertices do I see in the picture? Well, I see these two, and then I see all of these and all of these. So what can I say about these? Well, so first of all, I can just add however many vertices are in A plus however many vertices are in B, because they don't overlap. I'm assuming that they don't overlap. If they did overlap, then I would have to like do the number of vertices in A plus the number of vertices in B minus the number of vertices in the intersection, but they don't overlap. So how many vertices can we say there are in A? And keep in mind, I just need an inequality here. I just need greater than or equal to. Well, the degree of x is at least this. The degree of x is at least n plus 1 over 2. Keep in mind that the degree of x, that's the number of neighbors of x, including y. So if I want just a, then I should take the degree of x and I should subtract 1. So I'm going to write this, but I'm going to subtract 1 because a is really just the neighbors of x other than y. And then I'm going to, so that's how many are here, and then I'm going to add how many are here, and that's something similar, actually the exact same thing. And I add this all up, and it's a contradiction. I've got a 2 and a minus 1 and a minus 1, so that's nice. And other than that, I've got n plus 1 over 2 and n plus 1 over 2, and that just makes n plus 1. So we just showed that n is greater than or equal to n plus 1. That is a contradiction. So that means A and B do overlap. And now we're basically done. Letting W be any vertex in the intersection. We see that X, Y, and W form a triangle. Okay. Yeah, okay. So I have two more that I wanted to talk about, and I don't want to... Oh, okay. Yeah, I guess I was just not sure which one I wanted to do next, but I'll do this one next. Show that if the maximum degree of a graph plus the minimum degree of a graph is greater than or equal to n minus 1, and once again, it's a graph of order n, then G is connected and the diameter is at most 4. Of course, let me say one of the more obvious things about this, which is if we show that the diameter is at most 4, then that automatically means it's connected. So we can just worry about that part. So what this means is I have to consider any two vertices in the graph and show that there's a path of length at most 4 from one to the other. And this is potentially harder. I can't, like, it's not immediately obvious how I can use this concept of common neighbors because, if two vertices have distance 4, then they don't have a common neighbor. If they have a common neighbor, then the distance is at most 2. So if I'm going to talk about vertices of distance 4, then it may be not clear how I can use concepts like the concept of common neighbors. So let me start with a hint, and so first I would probably just pause the video and see what you can think of, but after you do that, you may want to take a look at this hint and then pause the video again before I give it away. So here's the hint. Let V be the vertex, or there may be more than one vertex, but there's at least one vertex that has this degree. This is the maximum degree, so let V be whatever vertex has the largest degree. Or once again, there might be a tie for the largest degree, and we just let V be one of those vertices. And then what we're going to do is show that the distance from U to that special vertex V is at most 2, no matter what vertex U is. So that's a hint, and so once again, I encourage you to think about this, and in particular, think about, like, this really gives you two things to think about. First of all, you have to think about how to show what I'm telling you to show. Second of all, you have to think about how does that help you prove the theorem, because that may not be entirely clear either. First think about how to prove this, and then think about how, if you could prove this, could you prove the theorem? So now I'll get into the proof. I'm going to follow the hint, of course. Let V be a vertex of degree delta of G, capital delta the max degree, and let U be any vertex in G. And what am I going to do? I am going to use this claim. This is the claim from the first problem of this video. Right, it's this claim that if you have a degree of U plus degree of V is at least n minus 1 in a graph of order n, then the distance is less than or equal to 2. Because we have that here. The degree of U is greater than or equal to the minimum degree the degree of any vertex is greater than or equal to the minimum degree. The degree of V is exactly this. And we're assuming that this plus this is greater than or equal to n minus 1. So here I have two vertices. The degree of one plus the degree of the other is greater than or equal to n minus 1. And by the claim that we already proved, that means the distance is at most 2. And once again, that uses the concept of common neighbors. A distance of at most 2, you can get a distance of 2 by having a common neighbor. And if you recall the proof of this, the proof, part of the proof was showing that that u and v have a common neighbor. But we don't have to think about that now because we're just using the claim. We don't have to reprove it. So we proved the statement in the hint. We proved that if v has degree this and u is any other vertex, then the distance from u to v is at most 2. So I proved the statement in the hint. But like I said, maybe we still have to think about how that implies the actual theorem, because for the actual theorem, we have to show that the diameter of G is at most 4. To show that the diameter of G is at most 4, I have to consider any two vertices. Really, it could be any two. So maybe let x and y be vertices of G. Then what do we know? I know that, before I fully give it away, let me kind of dance around the issue just a little bit more. The idea here is that I want to get from x to y in at most 4 steps. And I have this special vertex v that has a distance of at most 2 away from everything else. And it makes sense that since v has maximum degree, v can get to a lot of places. So it would make sense to go through v in my path from x to y. It's kind of natural to go through v because v has a high degree, and roughly speaking, that means you can get from v to a lot of places. So yeah, I think that's about as much as I can dance around the issue. So I'll just kind of tell you what I'm thinking now. The distance from x to v is at most 2 because the distance from anything to v is at most 2. So I can get from here to here in 2 steps. I can also get from here to here in 2 steps, and that makes 4 steps. And so basically that's it. Basically I'm done now. How do I want to say this more formally? More formally, I'm going to appeal to the triangle inequality. The distance from x to y is less than or equal to the distance from x to v plus the distance from v to y. That's the triangle inequality. I know this distance is at most 2. I know this distance is at most 2. And that gives me 4. So I just considered any two vertices in the graph, and I concluded that their distance is at most 4. Since that's true for any pair of vertices, that means the diameter is at most 4. And as we discussed, having a finite diameter automatically means it's connected. Okay. Now I just wanted to do another one that's like a sort of like an abstract question about graphical sequences. Just because I think there's some sort of common misunderstandings about these. So of course, people are pretty good at the specific sequences. Like if I give you a specific sequence, it just has specific numbers and you can tell me whether it's graphical or not. You did very well at that part, but then if it's more of an abstract question, like I tell you that a sequence is graphical, but it's maybe not a specific sequence. I just write it D1 through Dn, and you don't know what those numbers are. And then I ask you to prove that something else is graphical. People didn't really know what to do. So I thought I would do one like that. And like I was saying, we basically have two ways of showing that a sequence is graphical. One of them is just by drawing or describing a graph that has that degree sequence. The other is to use one of these theorems, like the Havel-Hakimi theorem that we went over, that just tells you to remove the first term of the sequence and then subtract one from the next several terms and do all that stuff. So let me tell you that for specific sequences, using the Havel-Hakimi theorem works very well. If it's an abstract sequence where you don't know what the numbers are, using the Havel-Hakimi theorem is typically not the way to go. Typically, if you don't really have a specific degree sequence, you want to think about the showing that it's graphical by describing an actual graph that has the degree sequence. So let's keep that in mind. So suppose we have a sequence, D1 through Dn, and it's graphical, and not all of the degrees are 0. Show that if we add a 2 to the sequence, and just to be clear, what do I mean by adding a 2? I don't mean adding 2 to one of these numbers. I don't mean you do D1 plus 2. I mean that I'm going to make a longer sequence. So the original sequence has a length of n. The new sequence is going to have a length of n plus 1. And the only difference is that it's going to have an extra 2. Usually we like to put degree sequences in order, so this is a little bit awkward because I don't know what these degrees are, so I wouldn't know where to really put the 2, but I'm going to put a 2 in there. There might already be some 2's in here, but then I'm just going to put an additional 2. So hopefully it's clear what the new sequence is. The new sequence has n plus 1 numbers, and the extra one that I put in there is a 2. So I can write it like this, but keep in mind these numbers aren't necessarily in order. Usually we put the largest first, so D1 would be greater than or equal to D2 and so on, but I don't, once again, I don't know where the 2 fits in, so I wouldn't know how to write it that way. So I'm going to write it this way, and I'm going to tell you that it's not necessarily in order. In any case, we want to show that that new sequence is graphical. So here's the idea I'm going to use. I'm going to describe a graph with this degree sequence. I know that there's a graph with this degree sequence, and I would like to take that graph and make a graph with this degree sequence. And one way to do that is, so this is just kind of scratch work. I can take, say, a graph, and I'll take an edge in the graph, and this graph probably has more stuff going on that I'm not drawing in the picture. There's more vertices and more edges. I just want to focus on this one edge. How can I take that and make a new graph, G prime, that has the same degree sequence but with an extra 2 in there? So there's going to be one more vertex. That new vertex has to have degree exactly 2. And other than that, all the degrees of all the vertices have to stay the same. Here's the idea for how to do that. My new vertex is going to be called, say, W. And I'm not going to have any edge from U to V anymore. Instead, I'm going to have an edge from U to W and W to V. So the new vertex, W, does have degree 2. I'm not going to make it adjacent to any other vertices. U and V still have the same degree, because if you think about it, I removed this edge, so that reduces the degree of U by 1, but then I put in this edge, so that makes the degree back what it was. And similarly, V loses this edge, so that decreases the degree of V by 1, but then I put this edge in, and that makes it back to what it was again. The other vertices, I'm not going to change anything, so those all still have the same degree. So that's the idea. I just have to describe that in kind of a more mathy, formal way. Let G have this degree sequence. Let UV be an edge of G. By the way, we know there is an edge of G because the D sub I are not all 0. If the degrees were all 0, then it would just be a graph that has no edges. And then so it wouldn't make sense for me to say, let there be an edge. But the degrees aren't all 0, so there's definitely at least one edge. So let this be an edge. Now let G prime have vertex set. Well, G prime should have all the vertices from G and a new vertex, W. I'm calling it W, and W is going to be the new vertex of degree 2. And now we'll just describe the edge set. G and G prime are almost the same. So I'm going to start just by describing the edge set of G prime. I'm just going to start by just writing the edges of G, and then I'm going to write how did we change it. Well, first of all, I removed the edge from U to V. Oops. Yeah, this is the set consisting of the edge UV. I shouldn't have written a comma in between the U and the V. So I remove that edge, and then I put in these two. Whoops, this should say WV, shouldn't it? then I'm just going to verify that this has the same degree sequence as the original one, but with an extra 2. W is the vertex of degree 2, and the first thing I'm going to say is for all the vertices except for W, they just have the same degree that they had before. The degree in G prime of X equals the degree in G of X. And that's just because if we're talking about a vertex other than U and V, then of course that degree didn't change because we didn't change anything out there. If we're talking about U and V, then as we discussed, the degrees are still the same. Even though we changed some stuff, we removed this edge and we put in these edges, the degree of U is still, it got decreased by 1, but then increased by 1, and the degree of V is the same. So those degrees are the same as what they were as well. Meanwhile, the degree of W is, of course, just 2. It just has the two edges that we talked about touching W. So G prime has the degree sequence in question. And so that sequence is graphical. So this is kind of similar to the one on the homework where we were given that a sequence is graphical and we wanted to show that another sequence is graphical, and the trick was to take the complement. This time we didn't do the complement. We did this trick where we add a new vertex that's sort of like, well, we take an edge and we replace it with like a path of length 2 from U to V. So this is a type of idea that you should have, showing that a sequence is graphical, is if you can start with a sequence that you know is graphical, and then make and start with a graph that has that degree sequence, and then make a change to that graph to make the new degree sequence what you want. So, okay, I think I'm gonna upload this now.